Hello.
Hello.
Yeah, you may begin now.
Mm.
Yeah, share screen and start. Should be working. Yeah, share screen. Should.
1 minute.
Yep, it is working.
Hello.
Yeah,
System on, right? Yeah. Hey everyone, welcome to KP classes. So today we will be teaching concepts from both computer organization and operating systems, which are taught together as a single course, Introduction in Computing to Computing. So the reason that I want to teach concepts from COA and OS together in a single lecture is because there are certain aspects of CO where if you learn those aspects and then learn about them in the software side, which is in operating systems, you get a better understanding overall of the concepts. So before I begin, I just want to inform you that I am also an aspirant for the GATE examination in 2026. So there is a possibility that I may make mistakes. So if that happens, then I'll definitely correct myself in the next lecture. So before we begin, I just want to let you know what are the prerequisites to be able to understand this lecture. So you need to be able to understand number representation. So number representation means how to convert binary to decimal or decimal to binary or understand how hexadecimal representation works. You should be able to understand this, for example, 0x6555, something like this, what it means. And if you even if you don't, then we'll have a brief understanding of it, but having a knowledge of this is very useful. And a basic idea of digital logic means you should at least know that a decoder will decode these inputs into four outputs, for example, 2 by 4 decoder, or a multiplexer will select the one of the inputs into it through a select line. These kind of things you need to know. Basically about multiplexers and decoders. So those are the two main digital logic components which are used in a processor. So yeah, so these two, if you have an understanding, then I think everything will go fine in this lecture as well. Okay. So the first thing which I feel is very useful to understand before you even get into computer organization is memory addressing. So before we get into memory addressing, what is memory, right? So memory essentially, if you recall from digital logic, it's a stored bit of information. So we store it in a D register, D flip flop, right? So that exact essentially becomes memory. So we have different kinds of memories also. So it's not like we only have flip-flop based memory. So there is a memory hierarchy which depends on how fast the memory is. So initially we start with the most fastest memory, which is registers. So this is the same as the register you have learned, D register. A register is just a collection of flip-flops. So if a D flip-flop can store one bit of information, then maybe you can combine eight of those flip-flops and you can store one byte. 8 bits is one byte, right? So the register is the fastest memory. Then after that, we have cache memory. So how is cache memory implemented? So we use something called static SRAM. So that is how we implement cache memory. This is the fast type of RAM where it is used, it kind of uses a flip-flop method only, but it's somewhat slower than registers. And it's also a little bit far away from the CPU. We'll get into cache memory, in more detail. And then after that, we have main memory. So main memory is implemented using DRAM. So DRAM is a bit different. This DRAM uses capacitors. So again, we'll get into this, when we talk about memory in more detail. But yeah, and then we have disk. So disk is less of memory and more of storage. So storage is when you permanently store. So all of these three memories, right? You only can persist them while the system is switched on. So once the system is switched off, you lose all of these memories, register, cache, and main memory. But the disk will allow you to keep that memory permanently on the disk. And when we refer to disk, we mostly refer to the magnetic disk. There are others now like SSDs, but we mostly look at hard drive. SSD is not in syllabus. Yeah. So these are the four main memory hierarchy. So, but deep down, or even though they are different, they are implemented in a different way. Logically, they are exposed in the same way as like in the same way. So logically, what does it mean by logically? It means that all of them are exposed as bits only. So they were exposed as containers of bits. This is known as the array representation. So every cell of memory is considered like an array itself. So if this is, let's say, for example, a bit, right? This contains a bit. Either it can contain 0 or 1, 0 or 1, 0 or 1, something like that. And this is the index of that array: 0, 1, 2, 3, 4, 5. So in the first block, in the zeroth block, this bit will be there. In the first block, this bit will be there. Second block, this bit will be there. Third and fourth, like this, something like this. So that is the array representation. So even though these memories are implemented in a different way, logically they will be shown to the CPU as if they are an array of contiguous memory bits or bytes. So that comes to another important point. Bits are the most fundamental unit of information, right? One bit is the minimum or the most atomic unit which you can store. You, sorry, you can't store less than a bit of information. But do computers have the capability to address or to find every single bit? The answer is no. So modern computers or modern CPUs, they address at the byte level. So addressing means finding, essentially. We want every byte in memory to have a unique memory address, right? So let's say if I want to find byte 5 in the full memory, so I need to have some memory address which I can read, which I or the CPU can read, or whatever is our system which is handling memory can read that memory address and go to that location where the fifth location, and find whatever memory is inside that and return it back. So that is the main use case of memory address. So when you have, so every byte of information should have a unique memory address. So if that's the case, like it doesn't need to be a byte. There are some CPUs which are word addressable. So word can be 1 byte, it can be 2 or 4. Mostly it is a power of 2. We do not have like 3 byte words. We usually have 1, 2, 4 like that. But modern CPUs like x86 or any Intel or any CPU right now which is used in your computers will be byte addressable, 1 byte always. Yeah. So that's the basic understanding of a memory address. Yeah. So I think these aspects are covered on this.
So this is a part of computer organization.
Yeah, yeah. This is a part of computer organization. So the idea is basically that all of our memory is stored as a contiguous array of bytes.
Hmm.
That is the main idea. Even though the implementation can be in different ways. So if we have RAM, then we actually have it as a 2D matrix, right? Where this is the columns, sorry, rows, and these are the columns. We have it like this. So even though it is implemented as a 2D matrix, our array representation makes it into a 1D matrix. So how do we find from a 1D address, memory address, this 2D, block? That is the idea of decoding of a memory address. So that also we'll get into a bit later. But the main idea is that no matter how the implementation of memory and what is the type of memory, whether it's a cache or a main memory or a disk memory, disk is stored as circular tracks, for example, right?
Mm.
Like this. So even then, these sectors, they are still represented as an array only, even though they are physically they are sectors, circular sectors. Logically, they are represented as an array of bytes itself. So every byte of the storage can be found. Usually, we don't do byte wise, but yeah, you can still do it if you wanted to. So that's the whole understanding of this array model of memory, basically.
Okay.
Any doubts on this so far?
Ah, no, no, we can continue.
Yeah. Okay. So now this was just an introduction into how memory addressing works. So one thing is, let's say for example, if one small question you can say, let's say if there is 64 kilobytes of main memory, right?
Okay.
So how much memory addresses would be needed to find 64 kilobytes of main memory? Like, is the number of memory addresses, like, would it be the same as the storage of the main memory? So 64 kilobyte, if you want, I can write it is 2 power 6 into 2 power 10 bytes, which is 2 power 16 bytes. Right?
Mm.
Each byte has a memory address. So 2 power 16 bytes should have 2 power 16 memory addresses. So when we look at it from byte perspective, because each byte should have memory address, we will have these many memory addresses, and that is fine. The number of memory addresses is the same, but we when we represent it in storage, we store memory addresses as well, right? Where else will it go? We need to store these memory addresses. Then the storage required for those memory addresses, that will not be 2 power 16. Why is that? Because 2 power 16 locations or 2 power 16 areas only need 16 bits to show, right? I mean, and let's assume this is 16, it's too big. Why does it need only 16 bits? Because let's say, for example, we have only 2 bits, okay?
Mm. Mm.
Something like this. So, what are the possible numbers I can show with 2 bits? 0, 0, 0, 1, 1, 0, and 1, 1. So, these are 4, right? Totally 4. So using 2 bits, I can show 4 locations. So that is basically 2 square, right? So
Yeah.
similarly, with 3 bits, let's say, I could show 8 locations, right? 0, 0, 0, 1, all that. So it's basically 2 to the raise, 2 to the power n, where n is the number of bits. So if it is 2 bits, then it is 2 square. If it's 3 bits, it's 2 cube. And if it is 16 bits, it is 2 power 16. So I don't need that much space to store the memory addresses. I only need 16 bits to find all of the memory addresses. So the size of my memory address, which is also called address bus, that would be, wait, let me just add this. Yeah. So the size of my memory address for 64 kilobytes of RAM, that would be 16 bits if it is byte addressable. Gate asks a lot of questions on this. So knowing, understanding how to find the memory, number of bits in memory, all of these things is important. Okay.
Okay.
Any doubts?
No, this is clear.
Yeah. So NDNS. So this is a unique property of systems. I think I'm not sure of the historical reason why it's there. Most people don't want it to be there. Actually, it's pretty confusing and not really necessity at this point. And most systems follow Little Endian system right now. I don't know of many big Endian systems. So all of our computers and even home appliances now follow Little Endian. But
Hmm.
it's important from a theoretical perspective to understand Indianness. So, one thing about Indianness which is misunderstood, I feel, by a lot of people, including me when I was studying, is what does Indianness apply to, essentially. So, before we get into what Indianness applies to, let's discuss different data types in a system. So, as I said, a system has byte addressable memory, which means every byte of memory can be addressed. But let's say I want to like I want to show some integer, right? Say for example 235 or something, right? So how many bytes of memory is 235 going to need? So one byte is 2 power 8, right? 2 power 8 bits. And we know that, you can do 1111 and you can convert that into decimal. But main idea is that this whole thing, sorry, one byte is 8 bits, not 2 power 8, sorry. So I'm saying that this number which is represented by 8 bits, we can write it as, say, for example, if there were 2 bits, so the maximum possible number is 1 1. So 0 2 1 2, so you get 3. Right. So with 2 bits you got 2 power 2 minus 1. So with 8 bits you will get 2 power 8 minus 1 as your maximum number, which I think is 255. So the maximum number you could have got unsigned integer, right? For now, we look at unsigned only. Unsigned means that these are positive numbers. So the maximum unsigned integer you could have got with 2 power 8 minus 1 is 255. So obviously that's too small. So usually, uh, like common integers cannot be represented with just 8 bits or 1 byte, right? We need more than 1 bit, one byte, obviously. So usually systems either have 2 bytes or they can even have 4 bytes, but mostly they have 2 bytes. So that maximum number is in that 2 bytes range of, uh, like 2 bytes of memory addressing, which you can use to store an integer. So even if the integer is small, by the way, like say 235 is pretty small, it can fit in 8 bits, it will still be stored in 2 bytes. So for this, you need to have an understanding of number representations. Let me just quickly give an overview of that. So if I want to store 235 in 8 bits, right? Then I can directly, just write, okay, 8 bits means it will store up till where? Till 128, right? We have 8 slots.
Hmm.
So 235 minus 128 we can do, we would get 7 and 0 and 1. So this would fit 1. Then 64 may it also fits. So this would be 43. Then 32 maybe it fits, right? So 1 1. But after that 16, correct, no, 128. Yeah. After that 16 it does not fit, 8 it fits, and 3 4 it does not fit, 2 it fits, and 1 it fits. So this would be the binary of 235, right? But I want to store it in a 16 bit or 2 bytes. So this is already fitting in 8 bits. So what am I supposed to do? So the first 8 bits which are there, 1 2 3 4, 1 2 3 4 5 6 7 8, they would have to be 0. And then we would start with this. This would go in the next 8 bits. So this is left padding of zeros. So we'll pad it up to the size of the memory address or the register or whatever, the number, so that we can fit it into 16 bits. But if a number is too big to fit into 8 bits, then it's a different problem. That's a more difficult problem. So if the number fits in 16 bits but cannot fit in 8 bits, then we need to split the number into two parts and manage that and handle all of that. Some CPUs have that, some CPUs don't have that to handle all of that. So usually we only consider like the biggest, useful size 16 bits, or if you take 4 bytes, usually integer is 4 bytes in modern systems now. 2-byte integers are there, but modern systems we have 4 bytes. So why am I talking about data types, right? And how does it relate to NDNS? Because except for ASCII characters, ASCII characters means A, B, C, these kind of characters, A, capital B, and 0 to 10 also can be considered ASCII. But except for these characters, which are 1 byte, every other data type, whether we have integer, whether signed or unsigned, it can be both. Or we have, uh, like, what else can you think of? Floating point or double. Double literally means double the bytes. So 4 bytes will become 8 bytes, right? Or you may have large int, something like this, some large integer type where you want a very big integer. So that obviously needs more bytes, right? So everything else is a multi-byte, more than 1 byte. And usually it is power of 2 bytes. So it is 4 bytes or 2 bytes or 8 bytes. It won't be 3 bytes. Nothing is 3 bytes. Okay. So these kind of data types, they are called multi-byte data types. Multi-byte. So for these special type multi-type byte data types, we have NDNS. So NDNS refers to the order in which the bytes of a multi-type, multi-byte data type are stored. So this is an important thing to understand because, yeah. So the order in which little endian and we have big endian, order in which bytes of a multi-byte data type are stored. Okay. So let's say we have an integer with 2 bytes, okay, just to make things simple. Say this is byte 0 and byte 1. So in the little endian system, little end, which is the LSB, which is the least significant byte, which is this byte,
Hmm.
that is stored at the front. Little end is stored at the front. So actually it will be represented in the system as 1 0, even though logically it is 0 1. Okay. So that is how little endian system works. So there's no understanding for this, it's just a convention. And big endian is the opposite way. So big endian is big end is stored first in big endian. Now I have one question. Okay. So this order does not really matter because we have like uh mostly since all of the systems are now little endian, right?
Yeah.
Uh there's not an issue of that. Okay, wait 1 second. I think I also messed up. Little endian, the little end or LSB is stored at the lowest memory address. Yeah, that's what I was thinking. How could it be the other way? Yeah, yeah. I'll just clarify again on this. I mean, see, this is the thing. Everyone forgets what is the order. Little endian is the least end or the little end, which is the LSB. Little means the LSB, least, is stored at the lowest memory address. So one way you can remember, which is how I also realized I made a mistake, is that little endian follows the normal convention. So what do you think is the most uh, basic or the simplest idea, right? You obviously, if you're having an array representation of memory,
Hmm.
right? Wait one second. If you have an array representation of memory, so as you increase the bytes, say as you increase your number, let's say if you have a number 1 0 1 0 1 0 1, something like this, right? 0. So if you increase the number 1, you want to go to the next slot in memory, right? If you
Yeah.
make this 0 into 1, you want to go into the next slot. If you make this 0 into 1, then it is a you need to go into the next slot. So as you increase the size of the number, you want to keep going in further slots. So little endian is the more intuitive way of doing that. Whereas big endian is storing in the opposite way, where the LSB is stored at the top and the big MSB is stored at the bottom. So every time you increase the LSB, you are not actually going further ahead, you're jumping instead, right? If you increase the LSB, you would jump in that array to some other location in the array. So that way you can remember that LE means that it is at the lowest memory address, is the little end is at the lowest memory address. So or else you can create some kind of mnemonic. Little means L, least, lowest, and end means at the end, right? At the end. So you can remember like that also. But yeah. Okay. Now my question is, say I have a character string r star a something is equal to kp classes. Okay. Uh, Tell me what will be the how will this KP classes be stored in little endian system and big endian system if I have this string?
In a string, like in Little Indian, it'll just be stored like normally, right?
Normally, as in K
Like,
first, then P, then K, right? Like this.
yeah,
And in big endian,
should be reversed. SESS. Yeah,
yeah. So this is a misconception. This is not correct.
this is not correct.
Yeah. So this is what I want to emphasize on this part, okay, of the
Little and
endianness.
multi-byte data type are
Yeah.
stored.
So I told you that in modern systems,
Hmm.
characters are ASCII, right? And
Yeah.
ASCII is 1 byte.
Yeah. So you're saying there can be multiple characters too.
No, no, I'm saying that in a string, yeah, yeah, kind of. In a string is not a multi-byte data type, right? String is not a data type. String is an array of characters.
Yeah.
So it's an array of 1 byte data types, correct?
Hmm.
This endianness does not apply to this. It is stored like this only. It is stored in the. This is not because of endianness. It is stored like
Because
this,
it's
but
not
it's
a
not because of.
contiguous. It's not a contiguous memory. It's just single.
It's not. Yeah. It's no, no. It is a contiguous. It's a contiguous array of
Like,
bytes, but it
but
is
each
not.
has unique this thing
Yeah.
addressing.
Each. Not even that. Each. It's not about addressing or anything. This endianness concept applies only when you have because we have data types, right? which
Hmm.
are which can have multi bytes. So NDNS applies only to them. That these data types which are multi-byte, it does not apply to an array of data. So
Okay. Okay.
even if this
Yeah.
was even if this is multi-byte and you have an array of them, let's say an array of integers, big endian will not make everything reverse. It will only make the bytes inside that
Each
integer
of
get
the
reversed.
cells. Yeah. Okay.
Yeah,
Okay.
yeah, each of the cells.
Yeah.
So one problem by gate on endianness, we'll just quickly solve that. Uh, 2 byte unsigned integer. So let's say that this first byte contains x and the second byte contains y. So if it's little endian, then we'll just follow this order. So any order doesn't matter. So I'll just read the question. If the numerical value of 2 byte unsigned integer, which is this, on a little endian system is 255 more than that on a big endian system, which of the following choices represents the unsigned integer on a little endian computer. So if the little endian system is XY, then the big endian which should be the reverse, right? YX.
Yeah.
So we are saying that this 2-byte unsigned integer, when we read its binary representation, it is 255 decimal. This is decimal. If I converted this binary in the little endian system into decimal, that is 255 more, right? So using this idea, we could eliminate a few options also. How? Because if this is 255 more, then that means that this reversal should be a lesser number, right? Like, so if I started, if I started with say 0x6655, no, 6665, then this is 6665, yeah. This is y and this is x, right? And we are going to reverse it 6566, and we are saying that it is 255, like this is 255 more. So this is correct. But if we reversed, like say C, I think if we reversed B, wait, one minute, just clear out this. If we reversed B, 0001, this if we reversed it, it would become 0100. So now this number is obviously bigger, right? Because 1 is at a higher location than this. So this cannot be the answer because this number is 255 more. So this big Indian one cannot be this answer. So like
Hmm.
that, this B option will get eliminated because it's an option which is bigger or which is smaller already than the big Indian representation. So this
Yeah.
cannot be the answer.
Yeah.
Similarly, 4243 also, the reverse is going to be 4342, which is bigger again. So this also cannot be, right?
Hmm.
So we are only left with A and D, and let's check it ourselves, right? Whether it is A, because it says it's a multiple correct answer, so we can't eliminate others. So we'll do the checking for that. But these two, if we eliminated fast, so we don't need to check. So now we have 0x6665, and in big endian it is 0x6566. So really the only difference is between these two by bits, right? 6, because, and this maybe these two as well. So we'll check these two in particular. So if we try to, like, I don't want to solve out the whole thing, like calculate the full number, because that takes a lot of time. So the best way to do that, to do this, is recognize that every digit in the hexadecimal representation corresponds to 1 in 16 numbers, right? So 6 here is going to correspond to from 0, 1, 2, 3, 4, 5, 6, similar to how binary of 6. So it's not going to change. Only when you reach A, B, C, D, then you have to see, how it changes. But 0x6665 may say this part we don't want to check only. This 6 and this 5. So 6 will become, I think, 0, uh, 0, 1, yeah, 0, 1, 4, yeah, 0, 1, 1, 0 it will become. So 0110 will be 6, and this will be 0101 5, this part.
Hmm. Hmm.
And we didn't see the previous 4 bits, right? We didn't even see them. And this next also we don't need to see, both are 0110. And now here we need to see because 00, 0101, 1 minute. And this is 0110. Hmm. So now we need to see if this is 255 more, right? So really the only difference here is between this one and these two. So these also, the whole this decimal, no, sorry, this hexadecimal is representing how many bytes? 2 bytes. right? This 6 6 and this 6 5, out of which 4 bits we have already ignored. 2 bytes is 16 bits. So 4 bits we have already ignored. So we've ignored 2 power 15, 2 power 14, 2 power 13, 2 power 12, and 2 power 11, 2 power 10, 2 power 9. So this is, or better than that, this is a bit complicated. Better than that, we can start from back. So back is, uh, this is 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, right? So this would be 512 more, but this 256 will get subtracted because this is 256 more, right? And this is one more. So there also one will, plus one will get, not plus, minus one. So this is 256 minus one, which is 255.
Hmm.
So this is 255 more. So this is correct. Now this is more easier to read than this. This was a little bit difficult to read. So everything is in 0 and 1 only. So we can just directly write, okay, this is 0 0 0 0 0 0 0 0 0 1, 0 0 0 0 and 0 0 0 0. And this is 0 0 0 0 0 0 0 0 0 0 0 0, and this is 0 0 0 1. So obviously the only difference is between this one and this is at the 256 point only. So that is fine. And this 1 is increased, so it would be 256 minus 1. This would be plus 256, this would be minus 1. This is 255. So this is also correct. So these are the answers. So we could eliminate these two and we only had to solve for these two. So these kind of techniques are always useful for understanding problems. Okay. So NDNS is covered. Uh, Now we want to understand how to decode. So I kind of gave a hint of this already, right? So we have a 1D array representation of a memory. Say for example, okay, so I can quickly give an example, right? So how would I represent 8 locations in a 2D matrix, let's say, which would be the best approach to do that? Let me think. One, two, three, four. So four, maybe I could do this a grid. So this is okay, not 8, say 16 locations. So this is a grid with 16 locations. So from uh, 1D, so 16 locations means first of all, how many bits will be needed for addressing all of them, all 16 locations? 4 bits, right? Because 2 power 4 locations. So in 4 bits, I can address this entire 16-bit matrix. Now, how do I decode this 4-bit address so that I look at some bits and I'll get what is the uh, row, and I look at some bits and I'll get what is the column. Then when I know what is the row and what is the column, I'll find the location, right? So that's the whole idea of bit slicing. So the simple way to understand how bit slicing works is to understand in a 2D matrix how are elements stored. So the idea is that they are stored in what we call row major order. So this is just a term. It's very simple. Okay. Row major order means we'll start at the first top here, zeroth row. We'll fill all of these, and then we'll go down and we'll fill these, and then we'll fill these, and then we'll fill this. So that's row major order. So they fill one by one in the row. If it were column major order, then we would start with this. Let me just, wait. Yeah. If we had column major order, then we would fill this column, then we'd fill this column, then we'd fill this column, and then this column. So both these orders are possible. But why do we want row major order will be very clear to you now when I explain. If I were filling starting from the first memory address 0000, where would it go? It would go here, right? This is the first possible 0000. Then 0001 is next, so that will go here. 0010 is next, that will go here. 0011 is next, that will go here. Right? Is it's clear so far? So like that, all of the 16 locations, it's clear, right? So far, any doubts? Hello? Yeah. So all of these four locations will go into these four in the top row, and then we'll go down and we'll go down. But now observe that, let's say we already knew this column is the zeroth column, right? Now when we are like, this is column is fixed, column has not changed, only these rows have been filled. So the only bits which we needed to represent that row filling were these last two bits, correct? These last two bits 00011011 would tell us how the row got filled. But these last two column bits did not change. So this last two bits have four locations, and these last two bits also have four locations. Now if I go into the first column, this last two bits will change, right? Because what, tell me what would be the next thing which will go inside? Like this is 0000, this would be 0001, and then this last one will be 0011. So the next one which will go has to be 0100, right? Which will go in this. So now these two bits did not change, and this has changed, and it has become 01. So observe that if we know what the column was, we only needed the last two bits to figure out where it goes in the row. And to change the column, we only need the first two bits to change the column. So we could slice the memory address, basically. We could slice the memory address, which is this box, that these two bits will represent where is it in which row, and these two bits would represent where it is in which column. So now if I give you a random address, say 0110, directly I can say, okay, hey, 10 means it is second, which means the third location, 012 here, and 01 means it is in this row. So automatically I got to know ki it is here, without having to count everything, count every byte and reach this point. So this access, this memory access or decoding this memory address became in O1 time. Means I can do it without, actually knowing the number of locations and all of that. It's not going to be dependent on the number of locations. So that is the benefit of storing it in this row major order. If you stored it in column major order, then this bit slicing would not be possible. So this bit slicing is very useful. So I hope you understood how bit slicing. Yeah. So if you know what is the array representation, right? Like sometimes it is in 4 cross 4, but sometimes it can be 16 cross 4, or it can be 8 cross 4, or anything it can be really. So once you know how many rows and how many columns are there, you just need to know how many rows and how many columns. So then you can use the bit slicing approach, where you say that the lowest bits will represent the number of rows, the number of columns, and this up to bits will represent the number of rows, most significant bits. I'll give another example. Wait, this will help you to understand. So, uh, let's say for example we have a 64 kilobyte RAM, which is storing, or let's not make it this complicated. Or okay, let's say it is 16 kilobyte into 4 byte, 4 bit. So that is 64 KB into 4 bit means there are 16 kilobyte. This is a RAM. Okay, just forget about that. This is a RAM, 16 kilobyte into 4 bit RAM. So what this would mean is that our rows are 4 bit and we have 16 kilobyte means that many number of columns, right? So now if we get an address, using that address we can easily calculate which byte will go in which location, because we know that the lowest bits will refer to the number. Okay, this will make it more confusing, I think. Let's just give I think 8 cross 4 memory. Okay, some 8 cross 4 memory, and we don't care about bytes and all that. So we have 8 of these rows. So let's say we drew a grid. We have 8 like that. These are 8, okay? And 4 we can directly write here. 4. So now 8 cross 4 means 8 rows are there and 4 columns are there. So there are 32 locations. So 32 locations can be represented in 5 bits, correct? 1, 2, 3, 4, 5. Yeah. Now, let's say I want to locate the byte which is in the third row and 0, 1, 2, say third column. Okay. So what does the third row mean here? Third row is we are always numbering from 0, by the way, in computer science. So 0, 1, 2, third row. So that is 2. So 2 is 1, 0. This is the binary of third row. And third column, that is 0, 1, 2, 3, which is 1, 1. Right. But one thing to keep in mind is that total number of columns are 8. No, my bad. This third row is this, right? So this will be 0, 1, 0. And this third column 0, 1, 2 will also be, yeah. This will also be 1, 0. Third column 0, 1, 2, right? So both are going to be 1, 0. But one thing to keep in mind is that the number of bits which we can use to represent rows are 3 bits, right? 3 bits. Because we have 8 locations. So 8 locations needs 3 bits. So we need to pad this 1, 0 with 1, 0. This I've already explained how to pad, right? Left padding. So now the idea is in how will this concept 0, 1, 0 and 1, 0, these numbers, how would they fit into this memory address? So I told you that the columns are decided by the lowest bits. So 1, 0 will go here. And the rows are decided by the top bits. So 0, 1, 0 is going to go here. So totally this memory address will find the third row and the third column, which will give me a unique memory location. Now is it clear? Hello. Okay. Okay, so using that idea, we can give a shot to this problem. So I'll just give you a minute to read it.
So two input address lines, 1A4 and is it IA?
Yeah, wait, let me give you the zoom diagram.
Okay.
Is it
Connected
it's
to the
visible, right?
yeah, yeah. It's visible, yeah.
Yeah.
Just show the question.
Hmm.
So are connected to the chip select port of these memory blocks. through a decoder as shown in the figure. The remaining 10 input addresses from IA11 to IA0 are connected to the address port of these blocks. The chip select is active high. The input memory addresses from IA11 to IA0 in decimal with the starting location of each block indicated as X1, X2. Which of the following options are correct?
Okay, you've
Hmm.
had a read of, I think, of the question, right?
Yeah.
Okay, so this seems like a very difficult question, but it's pretty simple actually when you understand how memory decoding works. So they have basically given a full memory address here, which is I think 11, so 11, 10, 9, 3, 6. Have they given the number? If it was 2, 1, and 0, that would have been 3. So 11 to 0 also has to be 11. So it's 11 bit memory address which they have given, right? IA11 to IA0.
Yeah.
So 11 bits can index. First of all, you try to see if a 4 kilobyte byte addressable memory is 11 bits enough to address it. No, no, it's not 11 bits, it's 12 bits. 210 is 3, right? So it's 12 bits. IA11 to IA0 is 12 bits. Is 12 bits enough to address a 4 kilobyte memory? First of all, let's first see if that is true. 4 kilobytes means 1 kilobyte is 2 power 10
Yeah.
bytes, right? And 4 means 2 square into that, so 2 power 12. So we got 12. So definitely 12 bits is enough to address this. But the addressing scheme is a bit weird. So they set it up in a little bit weird way. Rather than, the array contiguous method, which I told you, how
Hmm.
they are trying to deal with each kilobyte of memory in such a way that using some middle bytes, they are trying to find the block. So now you need to understand that. Wait, let me put a. This is a zoom diagram. So each of these bits from IA11 to IA0, excluding these I4 and I3, okay, we talk about these bits are indexing into the memory ka each location. So, like if you have the first location of this memory, then this IA11 to IA0 excluding these two. So I don't know how to say that. So we just say IA11 to IA0. This IA11 to IA0, if you make all of them 0, then it will index into one of these memories ka first location. Now which memory, that depends on these two bits. Okay. So if I took some address, let's say I took 0 0 0 0 0, let me make it simple that I'll put it as blocks of 4 zeros. Okay, so make it simple. 0 0 0 0 0 0 0 0 0 0 0 0 and 0 0 0 0, right? And this is IA0, IA1, IA2, IA3, IA4, and so on. This, yeah. So this location is going to go into the first IA0, IA1, IA2, IA3. This would definitely go into the first location of some memory here, some one of these memories. If you like, it would go into the first location. So it would be, according to this question, it would be a starting location. So they have given the input memory addresses of the starting locations. So you need to identify what are the starting locations of each block, right? So how are you going to identify the starting locations of each block? So all of these 11 addresses, like this particular IA11 to IA0 is how many bytes? 10 bytes, right? So this would be IA11, IA11, IA10, IA9, IA8, correct? This is following.
Yeah.
Yeah. And this would be IA7, IA6, IA5, and IA4. And this would be IA3, IA2, IA1, IA0. Now you tell me, or I mean, I'll explain whether this address is it a starting location of any of these memories. So for that, you need to understand how this memory is being decoded. We are taking these two bits, and we are using these two bits to check which block are we accessing. So if these two bits are 0 and 0, then the decoder is going to access the first memory address. If these two are 0 1, then the decoder is going to access this. If these two are 1 0, then the decoder is going to access this. And this is 1 1, decoder is going to access this. This you follow, right? Yeah. So now this is 0 0. So the decoder is going to access this. And everything else is 0. So these all bits are 0. So definitely this is also a starting location, because the starting location needs all of the bits to be 0. So this is a starting location and it is going to access this. So this is actually x1, right? This is x1 because this is the starting location of this. They have already mentioned in the figure that this is the starting location x1. So 0 0 0 0, all zeros are x1. So that is obviously 0. So I mean, none of the options are disallowing it. So we didn't really, eliminate any options. But I just wanted to tell that x1 is 0, right? Now x2, when we find x2, I think we'll be able to, get the answer basically, because other things are not really needed to solve. So how to find x2? X2 would come about if I4 and I3 are 0 1, because that's the only way you can get this memory in the first place, right? So I4 is 0 and I3 needs to become 1, right? Yeah, because see, 0 1, see, you know how a decoder works, right? I'll tell you how a decoder works. This is a 2 by 4 decoder. If I put in the input line 0 0, then this output would be selected. If I put 0 1, then this output will be selected. If I put 1 0, this output will be selected. If I put 1 1, this output will be selected. That's the basic idea of a 2 by 4 decoder. 2 by 4 decoder gives 4 outputs for 2 inputs. So this is a 2 by 4 decoder. 0 0 gives 0 0 output, 0 1 gives this output, this x2 output, and 1 0 gives this x3 output, 1 1 gives x4 output. So if I change to 0 1, I will get x2. Now my question is, do I need to change any of these bits? Do huh? No, I changed 4 and 3 to get x2, right? I mean, I changed 4 and 3 to get this memory block. You understood how that works? Yeah, no, because these 4 and 3 are decoding these blocks. So 0 and 1 will decode the second block, because 0 1 is 1, right? This is 0, this is 0 0, this is 0 1, this is 1 0, this is 1 1. 0 1 will decode this block basically. So now if I change 0 1, do I need to change any of these bits to get the starting address? Because the starting address is given by these bits, which are the remaining bits, right? IA11 to IA0 excluding 4 and 3, and all are already 0 here. So this will definitely give the starting address of this block, right? So I don't need to change, correct? So now all I need to do is to calculate the binary of this number. So what is the binary of this number? Sorry, not binary, the decimal of this number. No, no. Decimal of this number. This is 1, 2, 4, and 8. Now, this is the only one in the binary. 8. So we got 8. So in this only option which is 8 is C. So this is actually the answer, because we don't need to really solve other things. But if you huh? Yeah, this is the answer. Because x2 is 8, right? So mostly gate problems, you don't need to solve everything. So you only need to solve what is different. So in this x2 was different, so you need to solve x2. So now x3 starting address is, if you change this 01 into 10, then that is the starting address of x3. So using that, we can say that, oh, x3 is 16 because now 1 has moved in this direction. So x3 is 16. So that also matches. And x4, no, no, not a harder question. You just have to solve every memory block. That's all. I only solved the first and second, 0 and 1, right? Yeah. So seemed like a tough one, but it's pretty simple. I mean, you just need to understand that this is decoded into four blocks, and yeah. Okay. So this was the idea of memory decoding and all that. So this is actually not COA. So COA, you need to understand all of this memory addressing. It is like a tool to understand COA. So using that, you'll be able to get COA. If you know memory addressing and decoding and all of these things properly, COA becomes simple. So we'll start now what COA requires and how it works. So before that, let's discuss what a program is. So we all used to writing some sort of computer program, right? Either a C program or Python or Java or anything. So those are written in high level languages. So high level languages are languages which are more simpler for us, which are they are more closer to English, and they also encode higher level things where with lesser lines of code you can write more functionality. But what actually will happen is, see, it depends on what is this type of language, whether it's an interpreted or a compiled language. But let's assume that this language is compiled for simplicity. So what happens is that a compiler will take your high level language and output a set of simpler instructions. So we call it instructions rather than assembly because assembly is the language, but the actual thing which the computer is going to see, which the CPU will see, are a sequence of instructions. That's it. They're not going to see, the CPU is not going to see anything else. So a set of instructions are simple things, right? There are majorly only four types of instructions. So I'll discuss what that four types of instructions are. But using those four primitive instructions or the four atomic instructions, you can write any program. All you need is to access memory, store back to memory, and do addition. So like do some logical or mathematical operation. So using just these three, you can devise any algorithm, any program, anything. So really all you can say, computer science is just a sequence of arithmetic and logic. That's it, nothing else. And memory, that is computer science. So all of computer science algorithms, programs, and everything which we have, what right now we are watching this video, all are based on just a set of super fast calculations, mathematical calculations. So that's the idea. So let's start with each of these things, okay? So instruction set. What is an instruction set? So similar like how we have a language, high level programming language. Similarly, even the low level programming language has a set of primitive instructions or a set of fixed things which you can do in that language. Like you can't go beyond that. So we will not dive too deep into the different kinds of instructions because that's not relevant for gate syllabus. But every CPU will expose a certain number of instructions to the system, which you can use to code. So that is the instruction set. So ARM, for example, has its own instruction set, which is the reduced instruction set. In fact, ARM's full form itself is Advanced RISC Machines. So RISC here is reduced instruction set. So uh, different CPUs will expose different instruction sets depending on what, how they are made and all of that. That's more of a, company to company thing. Each instruction in that instruction set will have a unique opcode. So opcode is just like how we have bits, right? So let's say if we have 16 instructions in the system. So then how many opcodes will we need? We'll need 16 opcodes. 16 opcodes can be represented in 4 bits. So our opcode value field will be 4 bits. So that is the idea of opcode. And Von Neumann model and expanding opcodes is a little advanced concept we'll discuss later. But hello, hello, 1 second. Hello, 1 second. Just hello. Yeah. So coming back to programs as a set of instructions. So uh, we have the Von Neumann unified model. So what does this mean? I can explain in more detail, but the basic idea I will explain this more detail in later slides. But the basic idea is instructions also need memory. So obviously, right? Because we just saw now opcode itself needed memory. So a full instruction will also need memory. So data which is used by those instructions, which is like, let's say for example, we want to add two numbers and those two numbers are stored in some memory. So we are getting those numbers from memory. So that is the data. So that data also needs memory and this instruction also needs memory. So one human thought, instead of keeping a separate set of memory for instructions only and separate set of memory for data only, let's make it so that instructions and data are in the same memory and we will address it, and the CPU will know what is an instruction and what is a data. So that to understand, CPU has made special, uh, way to read the instruction and see, okay, this is an instruction and not memory, and where is the instruction located. So all of that will come in more detail when we discuss the computer CPU architecture. But basically, instructions are also stored in the same memory. So there's no difference between the data and the instructions. They can be stored in the same memory. Okay. So common opcodes, like I said, there are four major opcodes: load, store, ALU, and return. So load basically means if we have a memory, it can be any memory for now, any memory, we want to find a location. So load is going to take from a particular location in memory. So in instructions, we refer to memory using M. Okay. So this you keep in mind. So M3, if I write, for example, this would be third location in this memory. So obviously it's not going to be M3, it's going to be M and a set of bits, right? Like we discussed, we'll give a memory address. But let's say it is 3. So load is going to take the value of memory from M3 and put it in the register. That's what load is going to do. So why are we going in registers? Why not directly work in memory? That's because memory is very slow and CPUs are designed to work only in register. So we cannot do mathematical operations directly on the memory. So if I am trying to do add two numbers, the final addition of those two numbers needs to happen in register only. There's no addition which happens or anything which happens in memory directly inside the memory. So the CPU will use the registers which it has to add those numbers basically. Yeah. CPUs operate on registers. So CPUs will never care about the memory. It will only get the memory from wherever it is stored, and it will put it in the register. Okay. So load we have dealt with. Store is also similar. Once we finish our operation, whatever is the value in that register will be stored into some value in memory, some memory location. So it's the reverse, you can say. And ALU operation is all of those addition, subtraction, multiplication, division, blah blah blah, all of that. And return is more related to functions. So we can explore that when we discuss subroutines and all of that. But yeah, these are the four main opcodes. So, like I said, CPUs operate on registers, which means that if you have any, you need to bring the data or the data from main memory into a register, and then the CPU can take the value from that register and do the operations. So, for this, we have general purpose registers. So, general purpose registers will store the data of from the memory when we execute the instruction. So we use register transfer notation for this. So basically what it is if we are doing a load instruction, we have a register say R3. So we number all our registers first, R1 to R, say 20, 30, anything. Our register number, we assume it is unlimited. Mostly it is unlimited. So if you are doing a load instruction, register transfer notation is something like this. M3, we will transfer the location of M3 into this register. So that is register transfer notation. If I wanted to store, then R3 value I'll store in M3. So it will be the opposite. So this is all. That's it about register transfer. Now, like I said, like we have always discussed, CPUs operate on registers. So how will CPU access the instruction? Right. Instruction also is in memory. So how does the CPU access the instruction which is in memory and operate on it or decode it, as we would say? So why would a CPU need to decode an instruction first of all? Because the instruction is going to tell everything what needs to be done to those memory locations. So the CPU needs to decode the instruction first to get the memory which is there in that location, and then to understand what needs to be done, whether some addition needs to be done or some subtraction needs to be done, any of these things, right? So the CPU will decide that. So for that you need to decode the instruction. So yeah, but we cannot decode an instruction directly from memory. We need to bring that instruction into a register as well, because like I said, CPUs operate on register. So we have a special register for this called instruction register. So first thing what we would do is when we read an instruction, we will bring the instruction into instruction register. Now I'll explain how that happens in more detail. First we'll try to solve this problem. So a processor with 16 GPRs, so general purpose register means GPR, uses a 32-bit instruction format. The instruction format consists of an opcode field, an addressing mode field, two register operands fields, and a 16-bit scalar field. So what this means is our instruction needs to have some number of bits for the opcode, some number of bits for an addressing mode, some number of bits for two registers, R1 and R2. This is op, this is addressing, R1, R2, two registers, and some number of bits for a scalar field, right? So we are saying that this entire thing needs to be 32 bits. And they've also said that there are 8 addressing modes. So for supporting 8 addressing modes, how many bits do we need? So from memory, we have already learned that we need 2 power n equal to 8. So n must be 3 here. So we need 3 bits to support the addressing mode. So this is going to be 3. The width of this is going to be 3. And 16-bit scalar field. So here automatically you get the width as 16. They've already mentioned. Two register operand fields. So they have not. They've said that there are 16 GPRs. So if there are 16 GPRs, then how many bits do we need to show the registers? We need 4 bits, right? Because 2 power 4 is 16. So each register will need 4 bits. So we already have got every split. 16 plus 4 plus 4 is 24 plus 3 is 27 and totally we have 32. So remaining must be 5. So the answer should be 5. Wait, yeah, maximum number of unique for every addressing mode. Okay, so this is also, this you should be reading as well. Maximum number of unique opcodes possible for every addressing mode. So does this mean every single addressing mode or all modes? Wait, let us find out. So sometimes gate questions can be vague on wordings. And they've also said maximum number of opcodes. So we have 5 bits, so that should be 2 power 5 equal to 32, right? So that's also there. So it must be 32. Yep. The answer is 32. So there are 5 bits for opcodes, which means unique opcodes can be 32. Of course, if each addressing mode we wanted to say, then it would be 4 because 32 divided by 8 is 4. Okay. Accessing and executing instructions. So here, what does this mean? Let's say uh, we know that instructions are also stored in memory and data is also stored in memory. So let's say, for example, we have an instruction and that instruction is stored somewhere. So when we write a program, so let's assume for a moment that we have already compiled a program and that compiled program is stored somewhere. So where is that program going to be stored? It's going to be stored in our long-term memory, which is in the disk. So what is going to happen is this is a concept in operating systems, but the operating system is going to bring the program into the main memory when it needs to be run. So once the operating system has brought the program into main memory, that program becomes a process. So this is I'll explain more in operating systems, but basically now that program has become a process. And in that process, we have the series of instructions which are to be executed. So every instruction which is to be executed also will have its own address because uh, at minimum an instruction needs to be 1 byte, right? Like it cannot be like an instruction is going to be less than 1 byte. So definitely every byte has an address, so every instruction should have an address. So we need to find that address, so and we need to store it. So it's pretty simple to find the address of an instruction because we know the address of the program, like we know where the program is stored, because obviously otherwise if we didn't know, how would we bring it into main memory, right? So we know where the program is stored. And by convention, the program's address, the base address, which is called, or the base register, or the base address, that is the address of the first instruction. So where the program is stored is the address of the first instruction of the program itself. So this is also a common theme in arrays in any data structure. The address of the entire data structure is always the address of the first element in it. So this is a very common theme. Like address of an array is the address of the first element, all of that. So you learn in C programming and all of that as well. But here also, the address of the program is the address of the first instruction. So the first instruction, the address is easily found. But what about the next instructions? So that is the duty of the program counter. So what the program counter does is it keeps track of the instruction address. So as we decode an instruction, we will obviously get to know how many bytes are there in that instruction, right? Because we are decoding it byte by byte only. Like my system itself is decoding. So we will have a system to count the number of bytes and tell the program counter, okay, these many bytes were there in this instruction. You jump these many bytes to go to the next instruction. So that is what the program counter will do. But one important thing to keep in mind is this mechanism is only true if the bytes of an instruction are different for each instruction. So let's say first instruction has 5 bytes and second instruction has 6 bytes, third instruction has 4 bytes, then we can't, like, we have to obviously have to keep count of the number of bytes and then tell the program counter, okay, this byte has to be sent and all of that, right? But what if our system, our CPU, our instruction set says that no, every instruction needs to have fixed number of bytes? So then it becomes much simpler because now I know that okay, this instruction needs to have 4 bytes always. There's no escape from that. I can tell program counter, you keep the program counter incremented as a prediction that next instruction is going to be the immediate next instruction. You jump by 4 bytes and keep, so that we won't waste one clock cycle for accessing, for telling you that okay, this is 4 bytes or 5 bytes or whatever. You just keep it incremented and you store it in the next clock cycle. So the idea is that in this type of instruction set, which is called a reduced instruction set, the program counter is going to store the address of the next instruction always. So it will give the address of the current instruction to the instruction register, and it will store the address of the next instruction. So yeah, program counter in hardware, this we'll see in the unified pipeline how it works. But in context of RISC and CISC, I have explained this. So in the context of RISC, it will store the immediate next instruction. But in the context of CISC, it will store based on what is the number of bytes and all that. Like that, basically that concept which I told you. Okay. So the next idea is addressing modes. So if we wanted to do simple addition of two numbers, then we don't really need addressing modes because addressing modes is more about accessing data efficiently and effectively, and as well as accessing our instructions effectively. So we don't want to have to write the code, like say for example you want to access the third element in an array, right? Are you going to first find out what is the first element's address and then do the math yourself, add 4 bytes or whatever is the data type size or the width of the data type into everything, and find the third addresses, the third element memory address manually, and then tell the register, or sorry, the compiler, or the compiler will send a program to the CPU for that particular memory address. No, right? You don't want to do that. You want to be able to use indexing nicely in an array and access the third element directly. Or let's say if it is not an array, if it is a string, or if it is some other element or a structure stuff, then you want to be able to use pointers to jump 4 bytes or 5 bytes or any number of bytes, right? You want a kind of indirection. So you want to be able to tell that relative to this address, I want to move some number of locations ahead and go to the next address. So I basically want to compute what an effective address is. I want to be able to get an effective address which is based on the current address or based on some other address. So that is the whole point of addressing modes. Addressing modes gives you the option or the ability to not have to list out every physical address every time. Rather, if you know one address, then you can access the other addresses. So this is the whole reason. So we want to compute effective addresses, we want indirection, and we want indexing. So that is the whole reason we need addressing modes. Okay. Now we have different types of addressing modes. Uh, we have the immediate operand, we have register, we have absolute, register interact index, base with index. And these two we will discuss when we finish discussing, you know, our other CPU instruction set. So mostly most CPUs follow RISC. We've kind of introduced what RISC means, that every instruction needs to have the same number of bytes, right? That is one feature of RISC. There are other features, but this is one major feature of RISC. So let's first discuss the simplest, which is immediate operand. So immediate operand is very simple. It says that let us not bother about registers, about memory or anything. Whatever maths we want to do, we just give the value of those two calculations, those two numbers in the instruction itself. So I can give the value of those two numbers directly in the instruction. Now, that is what an immediate operand is. An immediate operand is something we want to immediately add without accessing it in memory, going to memory, doing anything. We'll just take the value, the bit string itself, which is in the instruction, and convert that into a number and store it in a register. That is immediate operand. So immediate operand, problem with immediate operand is if a instruction is fixed to a small number of bytes, like 4 bytes, then we can only have a small number which could be our immediate operand, maximum say 6,500. It's like maximum 65,000, something like that. We can't have more than that for immediate operand. Register mode, that is a normal mode where we always store everything in registers, and we use addition using registers itself. So that would be register mode. Absolute mode, it's again similar to immediate operand. We don't have any memory addresses. We just have everything in registers, and we'll use those registers and get an absolute value, which will also be in another register, which we will then store into memory. So these are not interesting. These are simple modes. The interesting modes start from register indirect, index, base with index. So register indirect means when we do a calculation, we will first, like, we do not know uh, what, like, how would we do a calculation. We'll have a memory address, and we'll fetch the memory address into, like, we'll take the memory address and fetch the location or the value of the memory address from memory and put it into a register, right? But let's say we want to work with that memory address later on. We want to use that memory address to calculate other memory addresses, calculate an effective address. Let's say we have the memory address of the starting of the array. We don't want to keep on putting second or third or fourth element. We'll save that memory address, and every time we want to jump in the array, we'll add 4 or we'll add some number to that memory address. So that is the idea of register indirect. Inside the register, we'll store the memory address, and then we can access the memory from that address in the register whenever we want, right? So main idea of register indirect is that we will need two memory accesses to access it, because we need one memory access to the register to get the address, and we need one memory access to main memory to get the memory value. So that's the idea of register indirect. And index is basically array indexing. So if I want to find A1, I can tell R and then 1. So R contains the memory address, and 1 will tell, okay, jump to the next in that array basically. So how it knows what is the number, that is told, like that number which is 1, right? Like say for example, I have an array of integers, okay, equal to 1, 2, 3. And if I want to access R0, this memory address we know. I told you that the address of an array is the address of its first element. So R0 we already know. Now array 1 is just going to be R0, the memory address of 0 plus some number of bytes to jump. How many bytes? Whatever is the size of int. Size of int in most systems is 4 bytes. So our register index notation will be R4. So R4 will tell jump by 4 bytes. So that is index. And base with index is also similar. We have a base register which we have for everything. And then every time we want to jump, we'll jump using the base register. So that's the idea of base indexing with base. Auto increment and decrement we'll explain when we come to CISC instructions. But it's similar, it's like indexing only, except that rather than having to tell the exact byte number, right? We told that okay, 4 bytes you jump. We can now tell that okay, just jump by one location, two location, three location. So it's very similar to how we do in C program. In C program, we don't say jump by 4 bytes, right? We just say okay, do R3 or something like that. So same thing here. Okay. PC relative mode. So the PC itself stores some instruction, right? It stores the address of the next instruction. So instead of fixing or locking the register and locking the address of the program to some fixed address, we can lock the address of the program to the address of the program counter. So then anytime we want to shift the location of the program into some other location, all the system needs or all the memory which is needed, we don't need to change the change the physical address of that program every time. Basically, that's the whole idea of program relocation. We want to relocate the program without changing the program. So for that to happen, we make the address of the program relative to the program counter, so that anytime we change the address also, we only need to load the starting address, and then after that, because it's relative to program counter, we don't need to change every other address of the instruction, every other instruction address, because all other instructions after that are relative to the program counter. So that will remain the same. That relativity is maintained because all we are doing is translating, right? When even if we move a program to another part of memory, we are just adding or subtracting some number of bytes to move it, right, to that part. So if we keep it PC relative, we will not need to change every instruction's memory address to move it. That's the whole idea. So these we'll explore in more detail. Stack frame and subroutines, it's a little more complex. Let's talk about risk and sys. So risk means reduced instruction set. The idea of risk is we will reduce the number of opcodes which are available to make it simple and reduce hardware. Why does it reduce hardware? Because now I don't need that hardware to count the number of bytes, right, in the instruction. Because already I know that it is fixed. So now my program counter doesn't need to count the number of bytes. So that hardware which is needed to count the bytes, like some counter or something, that won't be needed. And that is very important also because the CPU has a very finite space and it needs to be very small. So having a very large program, like having a large counter or something like that, is just going to make it bulky. Which is why almost every system now is a RISC system and not a CISC system. But that doesn't mean CISC doesn't have any advantages. A huge advantage of CISC is that it maintains, allows you to have a huge instruction set. So, how does that help? A huge instruction set helps that with less lines of code, we can do more. It kind of becomes a mini programming language. But what people of RISC thought was that if we can prove mathematically that these primitive operations or these primitive instructions, load, store, add, are enough to do anything, to solve any program, then why do we need to have an expanded instruction set with more opcodes and with more complexity when we can just tell the compiler to follow our RISC methodology and give the set of instructions? So that's what they thought, that let the compiler be the one to do this work rather than sys giving a functionality similar to programming language. So that is the whole reason why RISC is now more favored. But one thing to keep in mind is that a compiler will give a huge program for RISC when it will give a very small program for sys. So in the earlier times when our memory was just in a few bytes or kilobytes of RAM, storage and all that, that was not acceptable, which is why CISC was more favored. But slowly storage has become very cheap. 1 TB also you can get very easily of storage. So now everyone prefers RISC. Okay, I think we can stop here and continue in the next session. I think this is a good time to stop. Hello.